Okay, so the main part of my conference paper is based on the behavior and design of duplex stainless steel circular section stub columns at elevated temperature. What I'm going to do first is try to put things into context by saying a little bit about the background of stainless steel, the material behavior at room temperature and elevated temperature, and then going into the numerical modeling and the parametric study, followed by the analysis of the results and design recommendations, and then summarize. So background. So cold form stainless steel hollow sections have been increasingly used in structural and architectural applications, and this is due to their corrosion resistance, aesthetic appeal, the ease of maintenance, and their low life cycle costs. Now, the most common stainless steel grades used in the construction industry are austenitic, duplex, and ferritic. And as shown in figure 1, where stainless steel circular sections are used in the entrance lobby at the Cordis Hotel in Hong Kong, you can see the application of where CHS has been used in buildings. Also, it's also been used in footbridges. So for example, in figure 2, you can see the helix bridge where circular sections have been used in the truss part of the bridge. So in the last 50 years, stainless steel has had a high growth rate, and currently around 13% of the world's production of stainless steel is used in construction. The dominant product form for stainless steel elements are called formed sections. This means that flat sheet material is plastically deformed at room temperature into the final cross-sectional shape. Stainless steel has been used in offshore and onshore industrial sectors where fire is a significant hazard. And little research has been carried out on the structural behavior of stainless steel elements in fire conditions. So the focus of this study is to look into the behavior and design of duplex stainless steel circular section stub columns at elevated temperature. Now, material behavior. So for material behavior at room and elevated temperature comparison, I have compared stainless steel, specifically duplex, as this is what this study is based upon, against the carbon steel. So the dark black line represents carbon steel and the dashed line represents the stainless steel. So if we look at figure 3, we can see that the Young's modulus and yield strength of stainless steel are broadly similar, but the form of the stress strain curve is fundamentally different. Carbon steel has a sharply defined yield point, followed by yield plateau, and then strain hardening later on, whereas stainless steel exhibits much more rounded stress strain response without significant strain hardening. And now if you look at figure 4, which is the stiffness retention factor, so this goes from room temperature all the way to 1000 degrees, you can see that stainless steel retains its stiffness to a much higher degree compared to carbon steel. And just adding onto that, so if you look at figures 5 and 6, the strength retention factors which have been compared, so the duplex stainless steel tends to lose its strength prior to 600 degrees. However, for the important temperature range for structural fire design, which is around 600 to 900 degrees centigrade, stainless steel retains its strength to a much higher degree than ordinary carbon steel, and that can bring some real benefits in certain applications. Now the numerical modeling and parametric study. So this study was focused on the behavior and design of circular hollow section stainless steel stub columns, and one journal was used from here et al. And table 1 summarizes all the specimens of the CH test. So 16 stainless steel sections were modeled using the finite element program Abacus to simulate the test. The measured geometry, the initial geometric imperfections, the material properties of the test specimen were used in the numerical model. So for validation, you can see in figure 7a and 7b where the experimental line is the solid black line and the numerical comparison is the dashed line, which shows the load versus end shortening for the CHS stainless steel column. You can see that the stiffness, the peak load, and the unloading of the FE model capture a very similar response to the specimen. Similar failure buckling modes were also captured, and the mean overall result of 0.978 and a coefficient of 0.062 was achieved. So after validating, the models were then used to perform parametric studies to generate further structural performance data on stub columns in fire conditions. So for this study, the columns were modeled isothermally, in which the stress strain data corresponding to a given temperature is assigned to the model, and a compressive load is then applied until failure is reached. Now the modeling parameters are duplex stainless steel being utilized, the reduction factors taken from the design manual for structural stainless steel. The temperature range is from room temperature and then 200 degrees, 400 degrees, 600 degrees, 800 degrees, which shows an increment of 200 degrees. Class 1 to 4 sections were classified in accordance to Eurocode 3. A local imperfection of T over 100 was used, which is the thickness, and then the end supports are fixed. So analysis of the results and design recommendations. So in general, the international design codes adopt similar design approaches for stainless steel and carbon steel structures, despite the significant difference in material properties. Therefore, in the current work and described hereafter, some of the specific design rules for stainless steel members at room temperature and elevated temperature are employed, with the most current elevated temperature material properties for stainless steel is used to investigate the fire design of stainless steel stub columns. So now we'll look at the overview of the design method. So the Eurocode utilizes a cross-section classification framework for the design of stainless steel CHS stub columns. The classification of the circular section is determined by comparing the cross-section ratio against the prescribed slenderness limits. The current American and Australian New Zealand specification adopts an elastic buckling stress method for the design of stainless steel hollow sections, with the only difference being the reduction factor known as Kc. Now, the continuous strength method is a novel deformation-based design method which was developed initially to exploit this additional strength after the yield point in ductile materials and to provide a more efficient and reliable design method than existing procedures. The CSM provides accurate predictions for the compressive resistance of stainless steel circular section stub columns at room temperature. The current paper focuses on the applicability of this method for the design of duplex stainless steel circular section stub columns at elevated temperature. Now, the steps to calculate it using the CSM method is firstly to determine the cross-section slenderness for the full section or the most slender element. Secondly, obtain the corresponding deformation capacity from the base curve. Thirdly, determine the resulting limiting stress from the material model. And then finally, to calculate the compression capacity is the limiting stress multiplied by the gross cross-sectional area. Now, the FE models are employed to examine the cross-sectional response of the CHS duplex stainless steel stub columns at varying temperatures. The accuracy of the proposed design method are assessed against the parametric study. All of the calculations are based upon the measured geometric and elevated material properties, and all partial factors are set to unity. So here you can see in the figures, which they present the FE compression resistance for duplex stainless steel CHS stub columns at elevated temperature normalized by the respective design loads against the D/T ratios at 5 different temperatures between 20 and 800. You can see that the graphs of figures A, B, and C are showing conservative results and are demonstrating high scatter. Now, this conservatism is mainly due to the fact that the design methods ignore the strain hardening in stainless steel and the employment of the 0.2 strength. Nevertheless, in general, the existing design method for CHS stainless steel cross sections are considered to be safe. However, there is a scope for improvement and less conservatism. And if you look at graph D, the CSM design method provides a high level of accuracy and consistency. Now, summarizing the results in terms of tabular results, the 3 existing standard mean ratios for FE resistance to the predicted design loads are high. They are showing relatively high scatter. And for CSM, it demonstrates that the design method is capable of providing more precise and less scattered predictions for the fire design of these members compared with the standardized methods in the design codes. So just summarizing, a numerical study was performed to examine the cross-section response of CHS duplex stainless steel at elevated temperatures. Developed numerical models were validated against test data provided in literature. The FE generated CHS stub columns data were used to assess against the existing design method and was shown high level of conservatism and scatter. CSM is also assessed as a more rational alternative design approach and indicate that the CSM yields more accurate, consistent and reliable compression resistance predictions for duplex stainless steel, and further research is also currently underway on using the design code of EN 1993 Part 1-2 and using the other 2 popular materials used in the construction industry being austenitic and duplex. Thank you. Thank you for listening.